Now I'm starting it. So, good evening, everyone, and good afternoon to sir. Uh, Today we are diving into a topic that not only represents the future of technology, but also the frontier of human understanding, which is quantum computing. From revolutionizing how we solve problems to reshaping fields like cryptography, drug discovery, and machine learning, obviously. Quantum computing is more than just a buzzword nowadays because it's the next big leap towards something which is really futuristic. Okay. And now it's my absolute honor to introduce a guest who is at the very heart of this quantum revolution, Professor Vlatko Vedral. Professor Vedral is a leading physicist, author, and a professor of quantum information at Oxford University, and also a fellow at National University of Singapore. He is widely known for his groundbreaking work on the foundations of quantum mechanics, quantum entanglement, and quantum thermodynamics. All of these topics are like the base of what we get through in the field of quantum physics. He has also published extensively in top journals, delivered talks around the world, and has also written thought provoking books like Decoding Reality, which deals with how the universe can be represented in the form of data, and everything could be a kind of information and shapes the universe. And finally, I would like to introduce myself and Zishan, who are the host of this meet. And we are the students of IIT Madras BS Data Science. This is a program which is very rigorous and is reimagining the higher education of the world class IIT curriculum, which is entirely online, making it accessible to passionate learners from every corner of the country. And with this, I would like to warmly welcome Sir Vlatko Vedral. And just guys, before starting, I would like you guys to please be silent during this session. Okay. If whenever you have a doubt, you could just raise your hand, and Professor would uh, greatly resolve your doubt for whatever you have. Okay. So yeah, on to you, sir. Whatever you want.
Thank you very much. It's always a pleasure to speak with young minds who are interested in this topic. Please feel free to interrupt me at any point of the presentation, and I'm happy to discuss this more.
Yes.
Also, interrupt me if you don't see the slides as I go through them. So I will try to be brief. So exactly as you said, the topic is extremely exciting to scientists in general, because for a physicist, it really asks the questions regarding the ultimate nature of reality. Even though it sounds like a very fundamental question, what are the elements of reality made of? It actually also impinges on the future of our technologies. And that's what's exciting here, that science and technology really work hand in hand. I always found this very interesting, which is the subtitle that I have here, which is saying that somehow quantum physics, which started exactly more or less 100 years ago, and it started as a quest to understand spectroscopy, the microdomain, atomic structure. Now, after 100 years, is actually starting to leave the micro domain, and it's going into the macroscopic domain. So the question of having technologies, fully functional, universal, large-scale quantum computers, for instance, is actually one and the same question as whether quantum mechanics is a universal theory of the world. Does it also apply to the macroscopic world, or is it only true at some scale in the micro world and then it fails? So that's why this is a very interesting topic to us. Now I'm hoping you can see the next slide as well. And I think more than any other theory in physics, quantum mechanics really in many ways resembles the theory of information. And that's what led me, and not just me, I think a number of other people, to speculate that maybe we should talk about the fundamental units in the universe, not in terms of what you traditionally do in physics, in terms of energy and matter. So basically, if you go to one of those typical dictionaries and ask what is physics, it will tell you something like it's the study of matter and energy. However, it seems to me that certain fundamental properties are much better understood in terms of information, because this way, in a way, unifies both energy and matter, if you like. We start to see energy and matter as just different instances and different forms of information processing, which ultimately is really all quantum mechanical. And that's what's very interesting about this topic. So let me say a little bit more about it. Physics traditionally really is, you can think of physics um, as, um, as an enterprise to really make predictions about the observations that we make in the world around us. And even if you look at classical physics, not just quantum mechanics, frequently it's phrased in terms of information as well. So namely, information about the state of the system becomes crucial. And then the information about the changes of the state of the system is the second type of information that you might need. In this case, I called it speed of processing. So if you tell me how much information you can put into a certain system, and if you tell me how quickly you can process this information, it seems to me that you've characterized effectively the fundamental physical behavior of that system. And interestingly, in the history of physics, we have various colorful ways of expressing this relationship between information and physics. And I mentioned here two physicists who extensively talked about it. Laplace is the famous one, who basically said in classical physics, if you give me all the positions and all the velocities of all the particles in the universe, then I can tell you exactly what's going to happen at any point in the future. So Laplace was trying to illustrate the fact that classical physics is completely deterministic. If you really have a complete information at any point in time, you can then evolve this information into the future to make predictions about the future. You can even evolve it backwards in time to tell you exactly what happened in. And Maxwell was another person who actually made a slightly different point. He said, if you give me all this information that Laplace requires, it seems to me, that's what Maxwell said, that I can actually then violate the laws of thermodynamics, second law of thermodynamics. So Maxwell was more concerned about the status of disorder, whether disorder is something that fundamentally needs to increase with the temporal evolution of the universe, or could it be that as we get more and more information about the state of the universe, that we could actually eliminate this kind of noise and uncertainty and disorder? And that's the point in classical mechanics somehow, that in principle can eliminate all of these things. And now what's interesting, and that's where I want to bring in quantum information. And I want to tell you about the fundamental difference that have between the concept of information in classical physics, which I think is summarized in this slide, that the states of physical systems are effectively like betting portfolios. You know, they contain various probabilities for various outcomes of any measurement you can think of that you might be performing in the future. And in that sense, you can think of the laws of dynamics in physics, be they Newtonian laws or ultimately Schrödinger's equation, if you like, in quantum mechanics. You can think of these laws as telling you how to update this kind of initial information in your portfolio. So if you're not performing the experiment now, but you perform the experiment in 2 hours' time, then these laws of physics really tell you how to update the information in the portfolio. And now comes the crucial bit, which is really the only thing that is maybe relevant to understand it at this stage and for my talk. is that quantum information, unlike classical information, unlike the information that Laplace talked about, is really inherently random. There is something fundamentally uncertain about quantum states and measurements that we make on these states. And that's what's interesting. And I want to show you one slide on that, which I think captures exactly why quantum physics really leads to a different kind of information processing. In some sense, and again, as we see in Laplace, classical information is somewhat trivial because it always arises due to our lack of knowledge. So Laplace says everything is perfectly deterministic. A certain event will either happen with 100% probability or it won't happen at all, zero probability. It's all or nothing, classically speaking. In which case, really, the information is somehow trivial in the sense that the only time you can have uncertainty in classical physics is if you didn't obtain a proper state of your system, if you have some information. But usually the fault is in you, if you see what I mean. The fault is not really in the system or in nature. However, with quantum mechanics, this changes dramatically. And actually, there is an inherent uncertainty in quantum mechanics that comes from the fundamental laws of quantum physics. And it's nothing to do with whether we are able to make detailed measurements and get detailed information. So quantum mechanics says even when you have all the information in the world, you're not going to be able to predict even the simplest quantum experiment. And that's what's beautiful about this. This is what prompted me really to think about the fundamental constituents of the universe as bits of information, bits of quantum information. I think that's the right way to think about it. And it's a very beautiful unifying picture. Let me show you what I have in mind. I'm here giving you a very simple quantum experiment that you can perform with any system. In a sense, you can use atoms, you can use photons, particles of light, you can use more complex molecules, you can use nuclei, you can use freedom polarization, anything you can think of, and that's the beauty of this, behaves in exactly the same way. That certainly is intriguing, that all information at the most fundamental level in quantum mechanics has exactly the same behavior and exactly the same set of properties. And let me describe it. So like I said, I'm using here a photon, I'm using a particle of light. They're very easy experiments to perform. But in fact, any object, as far as we've tested them, will do the job. So if you send a single photon through a piece of glass, and this glass, like any glass, has a probability to transmit the photon and to reflect the photon. What's interesting, and that's what quantum mechanics tells us at the fundamental level, this is possibly one of the most profound realizations in the whole of science, and it happened in 1926, 1927, and it goes under the name of Heisenberg's uncertainty principle. So namely, the fact that when you send a photon through a piece of glass, and you do this under perfectly controlled conditions, every time you do this experiment, you do exactly the same thing. You send the photon, the same preparation of the photon, you fire the same laser, you keep the same room temperature, all the conditions are the same. What quantum mechanics says is that you can never predict in each run of the experiment which way the photon will go, whether it will be transmitted or reflected. So unlike in classical physics with Laplace's demon, where Laplace says, if I have the complete information, if I do the same thing, then classical physics tells me the same outcome will happen. Here, sometimes you get detector 1 to click, sometimes detector 2, but there is absolutely no way in quantum mechanics. In fact, that's one of the key principles of quantum mechanics, that there is no way to predict once which of the two detectors will click. And so all fundamental experiments in quantum mechanics are uncertain exactly in this type. The interesting thing is that if you repeat the experiment many times, then somehow you get a deterministic behavior. Namely, you can predict the frequency, how many times detector 1 will click and how many times detector 2 will click. And if your beam splitter is a 50-50 beam splitter, which means the probability to transmit and reflect is equal, then you will see on average that half of the photons end up in detector 1 and the other half in detector 2. But the amazing thing, and this is completely, profoundly different to classical mechanics, is that you can never predict any single run of this experiment. So quantum information is very different. Now, how do we understand that? Let me show you a slight extension of this experiment, and this now will get us into quantum computing, quantum information, and all the exciting applications of that. And I will then briefly touch on that, and then hopefully we can have a nice discussion on this topic as well. If you now don't detect the photon, and that sounds very interesting, that the behavior is different if you choose to put detectors after the beam splitter, or you simply put two reflecting mirrors, and instead of detecting the photon, you recombine these two possibilities and you bring them to another beam splitter. And the question you ask now is, which way is the photon going to go now? So basically, it passes through the first beam splitter, it gets reflected of two mirrors, it is then impinged onto a second beam splitter, and then I put again two detectors behind this, and I ask exactly the same question. If I have two beam splitters, one after the other, what happens now? And again, your classical intuition that's based on this Laplacian logic gets things completely wrong. And that's what's interesting. Namely, classically, you would expect that if the first beam splitter is completely random, and if you put another beam splitter there, you can only increase the amount of randomness. You cannot get something less random. So if the photon goes one way after the first beam splitter, comes to the second beam splitter, then presumably it will randomly decide to go one way and the other. And the amazing thing is that this classical intuition fails completely here. So what happens in this case is in the image image B. What happens now is that when you put two beam splitters together, and this is something we call interference, is that the photon that comes in one way only gets detected in one of the detectors. And this is extremely interesting. So I put two random elements together, two beam splitters, one after another, and suddenly I get a completely deterministic behavior. Every time I fire this photon, it actually ends up in only one detector. And to us, what this means, and this is the key to quantum information, is that you should think of this photon during this experiment as existing in both of these states at the same time. So classically, you would say it's either been transmitted or reflected by the beam splitter. But quantum mechanically, it actually is reflected and transmitted simultaneously. And that's this famous concept of quantum superposition. So the photon really does exist in both arms of the interferometer at the same time. And this is exactly this immediately, if you think in terms of information, classically, you could encode with the beam splitter a logical 0 or a logical 1, depending on whether the photon goes one way or the other. But given that quantum mechanically the photon goes both ways at the same time, you're suddenly able to process the logical 0 and the logical 1 simultaneously. And you can see how when you scale this up behavior, if you have more than one qubit, more than one quantum bit, more than one photon, if you like, in this implementation, you can actually then get an exponential increase in terms of your capacity for computation. So the picture C only illustrates this idea back that if you were to interfere with the photon, if you were to put a certain opaque object in the way in one arm of this interferometer, then it's a bit like making a measurement to check whether the photon is in one arm or the other arm. Then suddenly you recover the classical behavior, and suddenly it's possible for detector 2 to click as well as detector 1. So it's very interesting that if you choose to measure the photon, you will really find it only in one of the two states. However, don't obstruct the photon, and if you let it evolve according to the quantum dynamics as we understand it, it will really explore both of these possibilities at the same time. And that's hugely interesting, actually. So I don't want to bore you too much about the details of this. I want to immediately say a couple of things that I find extremely interesting, and then maybe we can develop. We can have some questions and answers after this. So an immediate application of, and I think this became clear in this even late 60s, 70s, certainly in the 80s, with various people, is that you can actually now obtain a much more powerful computer if your bits of information obey quantum laws, namely if they are quantum bits, rather than if you just stick to the either or binary logic of classical physics. And so this is just a pictorial representation of what I have in mind, that if you have now 3 bits, classically, if you like, you would be able to, with a single computer now, you would be able to compute one of these numbers at a time. So if your computer is, this is written in a very abstract way, but let's say your computer is computing some function f, which could be something like multiply the input number by 5, whatever the operation, square the input or anything like that. A classical computer would have to take each of these inputs in turn, perform the functional procedure, and then output each of them one at a time in succession. And the beauty of quantum mechanics, and this is really a generalization of the previous experiment I showed you, you can in fact do the same thing with a few beam splitters in a row, where you are splitting your photon into 8 possible paths, and that can actually exactly implement what I have in mind in this slide. So quantum mechanically, you would get your 3 quantum bits to simultaneously be in all of these 8 states at the same time. So the number 0, 0, 0, 0, 0, 1, 0, 1, 0, and so on would all exist simultaneously in different branches of your quantum superposition. And when a quantum computer acts on this to perform logical gates, if you like, what it would do is compute whatever function you wanted to compute simultaneously on each of these inputs. So you can see how if you had only n, let's say n equals 100 quantum bits, you would actually be talking about 2 to 100 different numbers that you could process simultaneously. So even a modest size quantum computer, which is something that we almost currently have, I think various places are announcing quantum computers with roughly 100 quantum bits, with which they can do quite remarkable computations, prepare remarkably quantum states, in the sense that they're extremely different to anything that exists out there in a classical computer. Already that has the capacity which certainly exceeds anything that a conventional computer can do. So that's really the key property that we are utilizing here. And there are a range of applications that are possible here. Now, I will show you another implementation. This is really just for the completeness, and I think this is an implementation that probably appeals to most of us in physics, because it's an ab initio, it's a bottom-up approach. And I think this is an experiment that's by now quite old, actually. This picture may even be more than 20 years ago, which are simply beryllium atoms. I call them ions here because an electron has been knocked out of each of them, so they actually tend to repel each other. And the vibrations that you see here, this is a real image from a lab where you target them with laser light. They absorb this light, re-emit it, so you can even see individually each of these atoms. And if you disturb them, if you shine the laser light in the right way, you can actually make transformation on these atoms that implement various computations. So you can actually do interesting things even with a handful of atoms of this kind. This to me is amazing. Of course, this image has been enlarged massively, as well as the frequency with which they vibrate is being slowed down, of course, for us to be able to see it. I think the oscillations are roughly 1 million times faster than what I'm showing you here. But the basic idea is that each of these glowing atoms on its own could actually encode one quantum bit of information. And because we can address them individually, we can resolve them spatially, we can actually then do gates in which we excite one of these atoms, change the state from 0 to 1, while all the other atoms remain unchanged. And that's extremely interesting. So here is the picture that illustrates that. If you think of the electron in this atom encoding this quantum bit, if the electron is closer to the nucleus, you could think of that as 0 logical state. Whereas if the electron is further away, you can think of that as a state 1. And then if you shine the right frequency that matches the energy difference between these two states for the right amount of time, you can send the electron from the state 0 in this picture to the state 1. So you move it being closer to the nucleus to being further away from the nucleus. And the interesting thing is, if you do exactly the same for half the time, you will actually make a superposition. This is what it says here, coherent superposition of states 1 and 0. So the same thing that we did with a photon and a beam splitter, and we put a photon in 2 different locations at the same time, we are now doing with an electron inside the atom. And again, the big question for us in physics is, does every object in the universe behave exactly this way? And again, so far the answer is yes. Anything we have been able to test really behaves exactly this way. And I think this is hugely interesting, and I will make a very brief comment on that in a minute as well. So I don't want to bore you, like I said, too much, because I think it would be nice to have questions and answers as well. But what I want to say as well here is that the exciting thing about quantum physics leaving the micro domain of atomic physics and going into the macro domain is that now we are starting to realize that actually small kinds of quantum computations even take place in the natural world. So a while ago, I was actually surprised to realize that some magnetoreception mechanisms that are present in various animal species. Here is a bird actually on this image that does that, but in fact, there are many more animals capable of that. And I don't want to go into the details of this, but it's a hugely exciting story. It turns out that entanglement, the key quantum effect, where you have two systems which are both in a superposition at the same time, this effect seems to play a role in how animals can tell the direction of Earth's magnetic field. And this was a big surprise, actually, that a mini version of a quantum computation seems to be taking place in a species of like this one, like the European robin. But like I said, many other species are known to be using similar things. Another thing that's frequently discussed, just to go very quickly through a handful of examples, is photosynthesis. That actually the way that light is converted into energy by plants, by bacteria, in fact, in this case, also relies on a certain process which is fundamentally quantum mechanical. And again, I will just give you a very superficial image of what's going on. But there is a transfer when light is absorbed by the bacterium. There is a very narrow, almost one-dimensional quantum wire, which then conducts this energy from the place where it's been absorbed to the place in which it triggers a chemical reaction, like an ATP cycle, which generates energy. And the interesting thing is that the hopping of this energy, and we have a lot of experimental evidence that this is of this kind, the hopping of this energy inside this nanowire is genuinely quantum mechanical, in the sense that energy goes in a superposition. It explores many different paths to get from the antenna to the reaction center. And it's something that classically would be extremely inefficient, suddenly becomes quantum mechanically extremely efficient, near 100% efficiency, actually 95% and higher efficiency, simply because it's very like a specialized quantum computation. What this molecule does, it seems to us in nature, is perform like a search algorithm, where basically the photon that's absorbed is looking for the most optimal way of getting into the reaction center. And that's really what bacteria and plants seem to be optimizing. So to me, this has always been a fascinating possibility. And actually, quite a lot of my research, that's maybe something that I can mention very briefly, is to go in this direction. I can show you briefly an experiment that we have been working on for the last few years, which is in fact to try to test whether you can even quantum entangle two living systems. So like I said, if we know that each of these living systems, like a bacterium, a simple bacterium, is capable at some level of handling quantum superpositions and very simple quantum computations, the question then is, can you really even use two such systems to entangle them? And I think this is a very brief sketch, which is simply saying, if you can trap two living systems in a very similar way how we trap the ions that I showed you before, and if you send a single photon through an interferometer to be absorbed by one or the other of these systems, then if you could execute this faithfully with a high with a high probability, you would actually end up with a highly entangled quantum mechanical state between two living systems, in which one of them would be excited and the other one wouldn't, and at the same time, vice versa. The second one would be excited and the first wouldn't be exciting. So we're really trying to go in the direction of Schrodinger's cat experiment. We're trying to ask questions: does quantum mechanics apply to macroscopic objects? Does it apply to the whole of chemistry? Do living systems like this, are they capable of quantum information processing? And are they capable of being in these entangled states? Now, I want to come back to computation, and I want to finish maybe with this. It brings me back to something that's known as Toffoli's thesis. And to me, this is hugely interesting because, again, it shows this universality, and it shows some kind of identity, if you like, between physical processes and computational processes. And that sounds like a fascinating idea. Again, it's very much in the spirit of the fact that how I started by saying that information is physical, and the different physical theories are underpinned, if you like, by different types of information processing. So I think this Toffoli's thesis is an amazing thesis, which says it goes well beyond universality that Alan Turing talked about, universality of all computers. This one says, forget about just computers. Could it be that any sufficiently complex piece of matter is actually a universal quantum computer? I think Toffoli thought in terms of classical, universal, just classical computers. But now you can upgrade this, and you can say, if I take anything, if I take a stone, if I take a complex molecule, if I take a living system, it doesn't matter what this is, so long as it has sufficiently many quantum bits, so long as it has sufficient capacity to handle quantum information. The question is then, can this entity compute anything that can be computed? And to me, that sounds amazing, really. It sounds amazing because we now know that we have to work very hard to make a quantum computer. We have to control the noise. We have to cool the systems down to very low temperatures. We have to shine light that's carefully selected, carefully fine-tuned for the right transitions. And this thesis says that maybe one day, when we realize how to do these things properly, then every piece of matter will be as powerful as every other piece of matter. Somehow it says that physics and computation will ultimately be indistinguishable, and that really sounds amazing to me. So the last thing maybe I want to say is that and again, this is another direction that I'm exploring as a physicist. Is I mentioned living systems being quantum mechanical, but there is another big question for us in physics, and I'm finishing. In fact, my new book is about to be published in October, which explores exactly these questions. What are the most exciting experiments we should be performing to really test all of these ideas? And I think the other big outstanding question for us is whether gravity is also quantum mechanical. Is gravity capable of behaving fully like quantum information? So if we take two genuine quantum bits and we really couple them gravitationally to one another, then will gravity understand the concept of superpositions, entanglement? Could you encode information in the gravitational field in the same way that we can encode information into photons, into electromagnetic field, and into atoms or any other piece of matter that we've experimented with? This is a hugely exciting question because we don't really have an answer, and there are all sorts of views out there in physics. So I think this development of quantum technologies will really not only lead to very powerful computations, but I think it's leading us now to be able to ask fundamental questions in physics and push the boundaries of our theories. And I'm extremely optimistic that within the next decade, we will actually even possibly come up with a new theory in physics that goes beyond quantum mechanics and general relativity. So that's actually what drives most of my research. But the beautiful thing about it is that it's really intimately somehow connected with information processing. So I'm going to stop here and thank you for your attention, and I'm happy to answer any questions that you might have. Thank you.
It was a really delightful session, sir. You presented us something that nobody of us like could engage with. I mean, it is engaging, but yeah, many of these things are new to us. I hope.
Thank you.
Yeah. So we are open to questions. If anybody has them, could raise their hands. Okay. Anshuman, Anshuman.
Yeah, I hope I'm audible.
Yeah,
Yes.
you are.
Okay, so I was just a bit confused between what is transmission and reflection. I need a clarification on that. Is transmission allowing the light to pass through, and reflection reflecting it back at 90 degrees, or somewhat like that?
Yes, that's a good point. In fact, the way you make a superposition, I only showed one way, in which case you had exactly what you said, that there is a possibility for transmission and there is a possibility for reflection. Um, there is there are many subtleties there where light actually goes inside as well and bounces back and forth, and you have to add up all of these amplitudes and all of the phases. But I think ultimately, the interesting point and maybe the relevant point is that all of these paths are explored simultaneously. And it really doesn't matter whether you think about it as reflecting backwards or going through. All of this is possible. You can really think even of light as being transmitted and reflecting backwards. All of these will lead you to the same kind of concept of a superposition. It's a very good point. Universality applies there as well.
Okay, so thank you. And
Okay, sir, I have a doubt that in the transmitter in which we pointed the beam at the detectors, right? So you
Yes.
said that the particles, when they change the direction, they could change the state like to logical zero and logical ones, right? So does that mean that the qubits or the particles which are there are dependent on the direction, the state, the quantum state is dependent on the direction?
Oh, beautiful question as well. That excellent. That too, exactly. That too is part of the information. So when I presented this as a single qubit, it's a very conservative view. It's the minimum you would get. You can actually think about different directions. In this case, a quantum optician would call these different momenta of light, the direction in which the photon is traveling. Each of these could encode a different bit of information. So in fact, you can get many qubits out of even a single photon by splitting it more and more and sending it in more and more directions. The only limitations here are really how well you can resolve these directions with your detector. And that's the difficult part. In fact, we have pretty good single photon detectors, but they are not perfect. So we have superconducting detectors, for instance, have more than 90% efficiency at detecting single photons. However, they could actually give you a wrong count. They could either misfire, so trick you into believing that there is a photon when there isn't one, or they could actually fail to detect a photon when there is one. None of this is 100%, but in principle, as far as quantum physics is concerned, each of the spatial directions could encode a separate part of information. So there is a huge capacity even in a single photon, actually. It's
Yeah.
very interesting.
Got it, sir. That's the same thing like you said in that lecture of University of London. Like you said that the any researcher is like will say that their theory is correct, like
Yes,
regarding any concept of quantum physics. So that's
yes,
the same thing with the quantum detectors, right?
yes.
Yeah.
Yes,
Okay.
and here you're right that this actually is another beautiful question, whether the detectors themselves could be described fully quantum mechanically. And again, I subscribe to that view. I think treating everything quantum mechanically in terms of quantum information is the right way to do all of this. But that's also interesting to test. We haven't been able, of course, to perform these experiments that involve superpositions of different detections and no detection and things like that. So I think that's what the future holds, probably.
Yes, sir. Sarang, you can ask your question.
Hello, sir. Am I audible?
Hi.
Right. Yes.
Hi. So my question was, could you just throw some light on quantum teleportation, and why don't we use Bell state measurements in this current scenario instead of uh, mirrors and photon capturing?
Oh, yes. This is a very good point. That actually, like I said, photons are possibly the easiest way to do some of these things. They are maybe the hardest ones to scale up. It's not clear that we can actually achieve a universal all optical quantum computer. There are companies doing that. There are people betting on that. The difficulty is exactly in your question, which is that if you want to have universality, you need to be able to have controlled gates between photons. So that means that the state of one photon needs to be able to change depending on the state of another photon. And getting photons to interact in this way is very challenging. A beam splitter won't do the job. And that's why, unfortunately, the beam splitter can only perform a partial Bell state measurement, but not a full Bell state measurement. So it's a very wasteful way of doing this kind of information processing. You would have to repeat your computation many, many times in order to build a significant fidelity in this way. If you, however, allow nonlinear elements, so that means if you couple your photons with carefully designed material bits, if you like, atoms, 3-level atoms will do the job here, then you could implement the Bell state measurement. And you're right, that's a key gate, not just for teleportation, but you can think of computation in this way as well. Because in teleportation, we think of teleporting quantum states. But in fact, what you are also doing is you are teleporting quantum gates. So teleportation, at the same time, interestingly enough, is also doing a quantum computation at the distance. And that's interesting. Another bit of universality, that actually sending information is in fact the same, if you like, as doing computation at the distance. And the problem with photons is exactly that we require much more intricate gates to get the photons to interact with one another. So I hope this answers your question to some degree.
Yeah.
Yes, sir. So, and what if we, so you say that it would cause some issues when we actually transport the quantum states from a location to the other. So,
Yes.
what if we implement some error correcting measures? Would that increase the overhead and slow down the overall procedure?
Yes, you're right. So that's exactly the way that the industry is going now, which is to say that it's exactly to increase the overhead, to increase the redundancy, and actually, even the most optimistic estimates are still extremely redundant in the sense that you're talking about more than 100 physical qubits required to encode one logical qubit. And for this to even be possible, each of these qubits needs to have a high enough fidelity of state preparation, measurement, and the basic gate operation. And no one at present is really below this level in all of these components. If you're not below the threshold and you attempt to do something like this, that means that your error will only increase, because each of these extra qubits will only increase noise. And so I think that that is the biggest challenge at present. It could be, by the way, this is always a possibility, that we find a more robust way of encoding quantum bits, which maybe doesn't require such low temperatures and such a high degree of control. You know, people frequently say, for instance, high temperature superconductors. If we really had a room temperature superconductor, then it would be quantum mechanical at room temperature. You wouldn't have to cool it down. And then, of course, this kind of platform would be perfect. It would be much easier to scale up. But at the moment, at present, we don't have anything like that. We are really going down to millikelvin, even nanokelvin, actually, for some of these atomic implementations. So these are thermodynamically, energetically very costly procedures. And that's why when you think about redundancy and achieving this kind of fidelity for 100 qubits, it seems like something that's still beyond our capability. But I wouldn't rule it out that we find an intrinsically more fault-tolerant platform, and I think this would solve all of these problems for us.
Thank you, sir.
Thank you.
Okay, Antram.
Yeah, so hello, sir. So I am currently a beginner to quantum computing, but I recently got an idea that if we try using the spins of electrons to actually using it as a binary, right? If it is a clockwise, then it is 1, and
Yes.
anti-clockwise, and 0. And if we try replacing the transistors which are currently used in the semiconductors to that by using optical tweezers, like
Yes.
we can actually isolate the atoms and then do certain experiments to actually see what the electron spins are, and we can also use it as like we can compute the angular momentum of the atom also, for
Yes.
viewing that it is spinning in anti-clockwise or clockwise. So
Yes.
are there any scope for that, or
I think
anything?
so. Yeah, I think it's a great idea. Actually, the quantum spintronics is a possibility, certainly. I mean, there's electron spin, so using EPR, electron paramagnetic resonance, but there's also NMR. There's the nuclear magnetic resonance. So, in fact, if you look at one atom, the picture that I showed was again extremely conservative. I was only looking at spatial states of the electron, and I only chose two energy levels, two different distances from the nucleus. But even a single electron, as you pointed out, has more degrees of freedom. We can talk about angular momentum. We can certainly talk about the intrinsic, the spin property. And it seems to me that this would give you a much higher capacity. The question again is to move away from the noise that's generated if you do these experiments at room temperature. So it seems to me that none of these technologies can be done in bulk and at room temperature. I mean, they can be, of course, they can be done, and NMR and EPR are done like that. But then the sample itself has a very, very, very tiny fraction, which you can think of as really being in a superposition, being quantum mechanical. So then people would say that spins of electrons and nuclei under normal circumstances are effectively as good as a classical computer. But if you really want to make a quantum computer out of that, again, you're facing cryogenics and similar problems as with atoms. But certainly, I think the good news is that even a single electron in an atom can hold much, much more information than one quantum bit. And I think all of these should be explored ultimately. It's an excellent point you raised.
Okay. Thank you, sir.
Sanskriti, could speak. Hello, Sanskriti. Okay, then Pranjal.
Ma'am, sir,
Okay.
am I audible?
Yes, you are.
Hi, yes.
Sir, I'm studying quantum mechanics now. So during this, so what are the most important concepts to truly understand before moving into this advanced topic like quantum computing and all?
Yes, I think probably on the mathematical side, linear algebra is the key thing. Simply because the states of quantum systems are best represented by vectors. And that simply comes from the superposition property that if you have two vectors, then a linear combination of two vectors is yet another vector. And that's exactly how it is with quantum states. Whenever you superpose two different states, you get yet another possible quantum mechanical state. And then operators, matrices in linear algebra, they're there to act on vectors and give you other vectors. So in quantum mechanics, they play a dual role, if you like. They play the role of observables as well as the dynamics. They're the ones that tell you how vectors change in time. So I think these are the key elements. But what I would really recommend doing is understanding this very basic concept of interference that I showed with a single photon, and trying to understand it in as many contexts as possible. So trying to learn quantum mechanics in terms of two-level systems, maybe rather than going through the traditional historical account. Usually we go through things like, black body radiation, Compton scattering, and so on. And then we arrive at the wave functions, the way the Schrodinger did it. We talk about the hydrogen atom, for instance, and so on. I think none of these things are necessarily directly. Of course, if you work with these things, you will learn about them sooner or later. But I think at the most fundamental level, realizing that all of these two-level systems behave in exactly the same way as far as superpositions and interference are concerned is maybe extremely important from the physics side of things. So try to go through the circuit, for instance, that I showed with a photon, and try to think what the equivalent would be with a two-level atom. Or take a complex molecule that can exist in two different configurations and think of that as a quantum bit. And then what would you have to do to this molecule to make it exist in a superposition? And then how do you recombine these superpositions to get the interference at the end? There are very few books that do quantum physics this way. I think one that immediately comes to mind is Feynman's lectures, volume 3. He basically introduces a sequence of different two-level systems. I think that's probably the best way of thinking about quantum mechanics.
Okay, sir, that's a great reply, sir. So before moving on to other questions, I would just like to ask you one question. That's what drove you towards doing research in the field of quantum physics and then into the quantum information part, which is like changing the world and changing the views towards what information is.
Yes, I think quantum physics, I think, fascinated me from the beginning. Probably not in my high school. I liked physics in my high school, but I think quantum physics was not taught very well, actually. So I think what captivated me in high school is more things to do with various bits of classical mechanics, thermodynamics, and things like that. But the first time I really learned quantum mechanics properly was the first year of university. And what really intrigued me are all the counterintuitive properties. There was the issue of tunneling, right? That a quantum system that doesn't have enough, that classically doesn't have enough energy to overcome a potential barrier, can actually quantum mechanically go directly through the barrier and show up at the other end of this. And in fact, all of these superpositions that we've been discussing, you can think of in terms of tunneling. You can even think of the photon as tunneling through the beam splitter and coming out at the other end. It's basically, at the level of mathematics, is exactly the same description as all other superpositions. And that really captivated me, that you could be coming towards, you could even be coming towards a very low potential barrier, like a bit like running towards a cliff, where classically, of course, if you jumped, you would certainly fall. You would fall down all the way. Whereas quantum mechanically, paradoxically, almost seemingly paradoxically, there is always a probability that you bounce back, even though classically the energy is telling you that you should definitely be pulled downwards. And I think all of this intrigued me a great deal. And it wasn't until I did third year quantum mechanics, I think that's when I was sure that I wanted to do this. And I think this is your second question. I learned about entanglement. And then I learned about the experiments that at that time to me looked amazing, which are basically to take a single atom, put it in a cavity between two mirrors, a bit like the experiments I was showing with living systems, but now you do this with an atom, and you couple a single photon. You get a single photon to be absorbed by this atom and then re-emitted. And I thought, this is amazing, because this shows you exactly how democratic, if you like, quantum information is. You could think about the atom as measuring the state of light, the photon, but you could equally well think of the photon as measuring the state of the atom. So if you get a click that you have a photon, you know that the atom is de-excited, it doesn't contain the photon. Whereas if you see the atom in the excited state, you know that the photon has now been absorbed into the atom. So then this kind of equivalence between the observer and the observed, I thought this is really mind-blowing, that you can equally say that matter observes light, and at the same time light observes matter. And it's all because of quantum entanglement, actually. Quantum entanglement is the key, as Schrödinger said. And I thought this was mind-blowing. Already then I started to do research into this. By the way, these experiments were given the Nobel. At that time, I didn't dream that this would happen. This was in 94, 95. I think in 2010, 11, 12, they were given the Nobel Prize, Serge Roche, for pioneering some of these quantum technologies. So actually, now we've done this with many more systems, and we know that things work in this way. But to me, this was captivating at that time.
Yeah, sir. I hope that you too receive a Nobel Prize. It's like I have read your readings, sir. Like your theory that every information, like every particle, could be represented as an information. Even the universe is like a whole, kind of quantum computer, we could say. So I just want to ask you something.
Yes, best image. Yeah, sorry, please ask me. Yes.
Yeah. So there is in this session, he told us that even though the first thing which everyone thought from quantum computing is that quantum computing and qubits, there are two types of bits, like classical and qubits, right? Yeah. So qubits are
Yes.
like undeterministic in nature. They could like be get in like different states. But in this
Yes.
session, you like cleared the doubt that yeah, at some point they could be determined. The nature and state could be determined, right?
Yes.
Yeah. So that's what fascinated me. But
Yes, it
someone,
is fascinating. You see that that you can think of it like this. I think it's really it's maybe the fundamental mystery how this can be in this way. That if you acknowledge that the simplest unit of quantum information is a single quantum bit, and it
yeah.
can hold at most one bit of information. That's exactly the definition. It cannot hold more than one bit.
Hmm.
Then if you know that your system, let's talk about the spin, for instance. If you know that spin is pointing up in the z direction, and now you ask, what does that mean about the x direction? If I choose to measure the spin in the x or y direction, this already tells you that because you saturated one bit, and this cannot do more than one bit, you don't have any information about any other direction. That's exactly your complementarity of information. If you know the information is in the z direction, then it must be completely uncertain in the x direction. So that means if you were to perform a measurement and measure the x direction of your spin, it's going to be equally likely to be x positive and x negative, pointing in the positive and the negative direction. And the same for y direction or any other direction. So that's the beautiful idea there, that if you hold already a maximum amount of information in one direction,
Yeah.
then that's it. You cannot have maximum information or any information in any other direction. But quantum mechanically, this means that your system has got to be in a superposition of states. And if you were to measure it in a different way, the outcome must be random, because you mustn't have any information about that. You've already used one bit of information previously. So that's maybe why I think that quantum physics is extremely close. It's almost identical to information processing in some sense.
Yes, sir. So that means one of the students asked a question that since qubits are like very indeterministic in nature, so
Yes.
there is no way possible way to store them, right? Someone asked this.
Yeah, good question. Maybe the way to put it is that you cannot copy them.
Yeah,
That's the interesting thing. And that's called no cloning in quantum mechanics. Absolutely. You can store them. You can store them faithfully. Quantum memory is not a problem. But you will always have to store the full quantum uncertainty. If you try to copy classical information in different directions, you won't be able to do that. You'll be able to copy one direction, but then because of complementarity, because of the uncertainty, all other directions will not be copyable at all. That's the beautiful thing. So somehow quantum information, unlike classical information, cannot be photocopied.
yeah.
Yeah.
So one more doubt, that since you know that quantum computers make the processing much more faster than any classical computers, right? So
Yes.
with that sense, how much energy does the quantum computers require? Like
A good question.
if I say
Yeah.
I am a student who wants to like
Good
use the
question.
Qiskit tool by IBM and just try to make a quantum computer myself, how much resources would it take?
Good question. It's a great question. Actually, it's linked to this other discussion that we had, that at present, it's extremely costly in terms of information. And actually, even classical computation is very costly in terms of energy and heat that's generated. And this is one of the points that's always discussed by industry, how to reduce this kind of energy cost. With quantum systems, it's even worse, because quantum systems have to be cooled down even more. So you're trying to make to utilize the fully reversible quantum behavior that happens at that level. And I think at present, that's actually the full cost. The interesting thing is that once you are at that level, if you say, how much does it cost to run all of these things? in principle, it shouldn't cost you anything because all of these transformations are reversible. And anything that's reversible, as we know, does not really increase the entropy. So once you're at that level, if you remain at that level, you are really mapping pure quantum states into pure quantum states. And in principle, this is frictionless. It's really like a superconductor. But to get to that level, to get to the frictionless level, you need to continuously invest. You need to
Energy.
pump out all of it. And that's the problem. And that's
Yeah.
extremely costly.
Yeah.
Yes.
That's a problem. Like the ChatGPT is also facing the big AI
That's it.
companies too.
Yes,
It's
it's
like,
exactly. It's interesting that somehow we are reaching the same problem, classically speaking, as you say. And again, if we could find an implementation that doesn't require all of this, it would be one way of addressing this issue. But at the moment, we don't have that.
yeah. And also, since the computation is much faster, so in cryptography, we try to encrypt the information, right, in the cryptography field,
Yes,
right? So,
yes.
kindly explain the threat so that the current cryptographic situation with the ongoing future advancements regarding quantum computing it could be dangerous or it could be like safe.
Yes, I think you're right that initially the big surprise came exactly from an algorithm, Shor's algorithm, that would actually make the public key crypto system completely unsafe. My feeling is that people who really worry about this and who care about encrypting things over very long periods of time, let's say more than 20 years, 50 years, typical governmental kind of documents, I think already with the discovery of Shor's algorithm, people have moved into even harder crypto systems. So in that sense, we know that there are ways of encrypting information that would be inaccessible even to a quantum computer. So that's one side of cryptography. Whether sending messages, again, in principle, we know that quantum mechanics can give you a higher degree of security than classical. But I think whether this becomes fully practical now depends on some of these practical issues that we're discussing. Interestingly enough, for instance, and I think this is again the fault of all our classical computers as well, in order to create states 0 and 1, even in our conventional computer, it frequently costs different amounts of energy. Because when you want to flip a bit, you may have to invest some amount of energy. So actually the state 0 and the state 1 are not symmetrically encoded, even in classical computers as far as energy is concerned. So in fact, one of the stupidest ways of eavesdropping on someone is to look at the energy output. You can literally just monitor the energy output and you can tell, in fact, you can read from that the sequence of zeros and ones, which doesn't sound sophisticated at all, but it is down to the asymmetry of encoding bits. So these kind of things could, of course, be improved with our quantum technologies. And we know in principle that we get a high degree of security. But again, this is all subject on the exact way that we implement this. Can we get rid of some of these frictions that require us to treat different bits differently and things like that? So there are many practical questions, which is why I think the industry is not fully on board. If you ask yourself, why is it that various banks or other institutions are not already using quantum cryptography, then I would say because in practice it's still not secure enough to overcome these difficulties. But one day it may well be.
So currently it is not secure enough, but one day.
No, definitely not secure enough.
Yeah. Okay. Now we can take some doubts of the students. Pranjal, you can ask your doubt.
Hello, sir. Am I audible?
Hi. Yes.
So I just started learning quantum computing, and I don't have a strong background in physics yet. But if you were in my place today, what exact path will you follow to master this field and build a meaningful career?
I think if you are interested more in the computational side of things, then I think what I said earlier probably applies even more, that I don't think you need to worry too much about the issues that one traditionally worries in physics. I would simply follow the models that involve quantum bits and quantum gates, simply like the circuit model understanding. Try to understand quantum computers as a computer scientist would understand them. In fact, one of my students, a number of my students, in fact, came from the mathematics and computing background, and they had absolutely no problem. Actually, it took them maybe less than a year to understand fully the relevant bits of quantum mechanics, and already then make original contributions and write papers, novel papers in the field. So I think you can be very practical. You can ignore the historical parts of quantum mechanics. You can ignore quite a lot of the debates that exist in quantum mechanics about the measurement problem, observation, all of these questions, because I don't think they're directly relevant for quantum computers. And I think if you just follow the circuit model, think of all of these gates as generalizations of classical logical gates, then it seems to me that you can very quickly understand the
Like
one of
helpful
my
to me.
students, she did the whole PhD, and just as she was about to have the viva, the final oral exam for her PhD, she came to me in my office and she said to me, "Listen, can you quickly explain to me what a Hamiltonian is?" And to a physicist, this is very funny, because Hamiltonian is the first thing you learn in quantum mechanics. It's the key function that we all use as physicists to describe dynamics of our system. But if you're a computer scientist, you don't care about Hamiltonians. You care about the quantum gates that change the states of your quantum bits. But you really don't need to even understand the details of how this is done in physics. To me, this was very funny. And actually, she passed with flying colors, and she's a professor now in Edinburgh. So no problems there at all to come from a computer science, mathematics, even engineering direction, and not worry about physics in too much detail, but really go directly and follow your own instincts and interests.
Thank you, sir.
Absolutely thought-provoking, sir, what you said. Yeah. Yes, you could ask a question.
Hello, am I audible?
Yes.
Yeah, so the question I have is a hypothetical question. It may be dumb if you want to call it out, but the question I have is, sir, that my question is, in the future, maybe 10, 15, 20 years from now, when we have a quantum computer powerful enough to compute anything we want, if the entire state of the current present universe is given to it, would it be able to predict future? And if it can, what does it imply about free will?
Good question. It's a fantastic question, because when I said that quantum mechanics is now going into the macro domain, one of the questions is exactly the one that you are raising. It's to do with the functionality of our brain, consciousness, and all that goes with that. The question of free will is immediately comes up in all of this. So unfortunately, it seems to me, this is the way I would put it, quantum mechanics doesn't, even though it seems better than classical physics in the sense that it has fundamental element of surprise. There is something you cannot predict or decide in quantum mechanics, even with the complete information. The problem, why this is still a problem for free will, is that it's random, really. Quantum mechanics says that the outcome is completely random, and randomness itself, if it's really genuine randomness, is somehow as bad for free will as determinism, because free will still somehow wants to achieve something deterministic based on the on the data that
Yes, sir,
that you
because
have.
randomness does not have will of its own, right?
Indeed. Randomness is like tossing a coin then and going down the path that the coin suggests. So to me, it is a very interesting question.
So,
So
what do
even though
you believe
quantum
as
mechanics,
a researcher, like you are studying this field so closely? What do you believe? Does free will exist or not? I, for one, believe that free will is a sort of a myth which we have made in our own minds. What is your take on it?
yes, I think I have a very similar take. I agree with you. I think the fact that we feel that we have free will is one thing, and I think that's undeniable. I think all of us feel like we are in charge, at least of some things in our life, and at least as far as the basic questions are concerned. What do I do now? Am I going to have one thing for dinner or another? Am I going to have a coffee or a tea, and things like that? You would almost certainly say, I feel like I made that decision. But in fact, if you look more deeply into the mechanisms behind this, none of this is anywhere to be found. All you find are really different biological mechanisms which function very similar. They're all remarkable, that's true, and they evolved in incredible ways, and they're frequently even more sophisticated than anything we can do still with artificial means. However, you do get a feeling that this is just simply the laws of physics unfolding. It is a form of quantum or classical, even at some level, computation. So I agree with you that it's very hard to see where genuine free will would enter. But I think it's precisely because of this that this is extremely interesting to study.
Yes, sir.
Yes, sir. Thank you.
Okay. So everyone, we are going to conclude this session because sir would be having his course also. So,
Thank you.
uh, sir, before going, I would just like to thank you for this insightful session that you uh, kept for us, even though your busy schedule. And from the basics of qubits and entanglement to the deep philosophical things that you told us here, and even answered our questions, even though they could be basic, even though they could be like
I
even
think they've
time
been great.
taking. Yeah, you explained them very briefly. And so for that, I thank you very much. And to everyone who joined also, thank you very much to all. And with that, uh, we hope that you have a great day, sir, coming up.
Thank you. You too. Thanks very much.
Yeah, thank you, sir.
Thank you.
We're
Bye.
delighted.